Hi, in this video I want to show how to write down Newton's second law in a rotating frame, which is from section 9.5 in the textbook. In section 9.4, the author shows how to relate generally the time derivative of some vector in a inertial and non-inertial frame. So just to remind you what that looks like, he says if we have some vector q, it could be any vector, position, velocity, momentum. We want to know what its time derivative is in an accelerating frame. So what we mean by that is this vector has components. So for each component of that vector, we want to take its derivative. And then to get that vector back, we have to add up over all the components, where we're going to multiply each component by its unit vector, right? And these unit vectors are fixed in the rotating frame, right? So these are the unit vectors that the rotating frame would use to describe its vectors, and so they are rotating along with the frame. And so what the author shows in section 9.4, the fairly reasonable result that in the non-accelerating frame, then, what the derivative of this vector would look like would be two parts. One is the derivative of the vector, the actual components of the vector, the same as what they are in the frame S. So if these actual components themselves are changing lengths, because everyone agrees on what these components are. This is just a vector pointing in space. It has a length, and everyone in every frame, they agree on what that length is. This isn't special relativity, remember? All right, so the derivative of this vector as seen from the non-rotating frame is going to be whether those vectors are really actually changing in magnitude, but then we have to add to it this extra piece that comes from the fact that the frame is rotating. And so this is our very useful relation that says that if you had a fixed length vector in a frame that's rotating, then from the non-rotating frame, its time derivative would be given by the cross product with the rotation vector. All right, so in general, if the vector q, it has components that are changing in time in the rotating frame, then in the non-rotating frame, this is how we would write down what that time derivative is. So now what we want to do is let's apply this result, to a position vector. All right, so in other words, we're letting q be r. And so what I want to think about is the time derivative of that vector. So that's, of course, the velocity, right? So I want to take the derivative of this vector. And in the non-rotating frame, right, I want to know what that derivative is in the non-rotating frame. And by this result up here, we know that the way we write that is it's the derivative of that vector in the rotating frame plus this piece here, right? Plus the omega crossed with the r. Okay, so fair. So that's how we would relate. So basically, right, this would be the velocity as seen in the rotating frame. And what this statement says is the velocity as seen in the non-rotating frame would be that term plus this piece coming from the rotation of the frame. Okay, so now what I want to think about is let's get the acceleration, which is the derivative of the velocity with respect to time, right? Which is, of course, the second derivative of the position vector with respect to time. And so again, I want to have this in the non-rotating frame. And so what I need to do now is basically apply this condition, or this result here, again, to this. So this is my v vector, right? So this is acting as q, if you like. I'm going to apply this result, but now my q is this whole thing because I'm trying to differentiate the vector v. So what does this thing say to do? Well, I need to have the derivative. I need to have the derivative with respect to time of this vector. So maybe I'll just write it out slowly that way, right? In the S frame. And then I need to take the cross product of the rotation vector with this vector. Okay, so let's say that. So now let's explore. that means is to take the time derivative of, what's my v vector? It's this, dr dt in the rotating frame plus omega cross r in the rotating frame. So all that has to take the time derivative of it. And then I'm going to add to that the cross product of omega with my v vector, which is dr dt in the S frame plus omega cross r. All right, so that's what I have to do. So let's go ahead and do it. Well, so I know how to do this derivative. This is just the second derivative of r with respect to time in the rotating frame. And then I've got to take the time derivative of this cross product. And way back in chapter 1, we showed that that works by distributing the time derivative into each of these vectors. So the result is d omega dt crossed with r plus omega crossed with dr dt. All right. And then over here, I'm going to get two terms. I'm going to get omega crossed with dr dt. And then I'm going to get omega crossed with omega cross r. All right, so hopefully you can see this, just that same term there, running out of room. And actually, it might be worth just reminding ourselves what we've just done over here. So let's go back a page, right? So what I'm figuring out is the acceleration, right? In other words, the derivative of velocity with respect to time as seen from the non-rotating frame. So that's the second derivative of the position vector with time. So let's just write that over here. This is the second derivative of r with respect to time in the non-rotating frame. Okay. So now we can do a little cleaning up here. First of all, we notice that, so here I have two terms that are the same, right? These are both the same term. So this is just 2 omega cross, and to save some writing, I'm just going to call this r dot, right? So it's the time derivative with respect to r, time derivative of r with respect to time. And what else can we do here? So we've got the derivative here. And then what we can do is we know from Newton's second law in our non-rotating frame, right? We know that tells us that the second derivative of r with respect to time is equal to, well, ma, which is equal to the sum of the forces that are acting on the object. All right, so this piece, right, the Newton's second law, the ma term, is sitting over here on the left-hand side. All right, so I'm going to substitute that in over here. Now, to do that, I got to multiply everything by m. So I'm going to multiply all the terms in this expression by the mass, so that the left-hand side becomes the sum of the forces. And then I'm going to get m r double dot, right? And I'll just emphasize that's with respect to the rotating frame. That's kind of what r double dot, the author doesn't actually make that distinction. The author says, from now on, when I write r double dot, what I mean is in the rotating frame. But I'll just put it there to be clear. And then we've got this guy here, which is m omega dot cross r. And then we have our 2 omega cross r dot. And then way over here, we have, I forgot the m. 2m, and then plus m omega cross r. All right, so that's looking a lot like a Newton's second law thing if we take this term, the ma term, and put it over on the left-hand side and put the force over on the other side, right? I can write it so that it looks like this. M r double dot equals the sum of the forces, let's do that right, sum of the forces minus m omega omega dot cross r minus 2m omega cross r dot plus, minus m omega cross r. Whew. That's a lot of terms in there. Let's just make that guy look a little better. There we go. Now, if you don't like all those minuses in there, then we can clean that up as well. We can say that what we have is mr double dot, sum of the forces. So remember, one of the features of cross product is if you exchange the order of the vectors, right? If you change this from omega dot cross r to r cross omega dot, it switches the sign, right? So I can turn this into a positive sign just by rearranging the order of the vectors here. So 2m r dot cross omega, vectors on these, plus m. Okay, now this one's tricky. What does it mean to exchange the order of these things? So it should be omega cross r crossed with omega. There we go. All right, so that's the result that we get. We get a Newton's law kind of looking thing in the sense that I have an MA over here. But remember, this is, again, I'll emphasize, this is the acceleration of the object in the rotating frame. So this is the acceleration that the observers in the rotating frame would see measured against their own coordinate system. And over here, right, we've got some of the forces. These are the actual forces that you can list and enumerate all the things that have contact with your object. Maybe gravity as well, right? And again, the observers in both the rotating and non-rotating frame agree about all those forces. And then there's all these terms here, which as far as an observer in the rotating frame believes, these are all additional forces that are acting on its object. And there's not much it can do about them, right? And so then we give these guys some names. This is the transverse force. So F tran. And this is the Coriolis force. And this is the centrifugal force. Notice, because there was just this sign swap by reversing the order of these vectors. And so some people define the force in terms of the positive value, so Coriolis force is r dot cross omega. Other people define it as being negative omega cross r dot, right? And they're saying the same thing. It's just what order you prefer to list your vectors in. Okay, so this gives us what Newton's second law looks like in a rotating frame with the emergence of these three additional fictitious forces that are arising because the coordinate system is accelerating, in this case rotating. And what we'll do in the next few days is explore what the features are of these forces. When do they come into play? What's their effect on the motion of objects? And so forth. And hopefully, just looking back over this derivation, again, all we've done is we've used this basic idea that the time derivative of a vector viewed in the non-rotating frame is the time derivative of the components plus this term coming from the rotation of the frame. And we had to apply that twice. First, to find the velocity vector from the position vector, and then applied on the velocity vector to find the acceleration vector. And so we got a lot of terms in there, but we were able to simplify them down to this form here. Okay, so the rest of the week will be spent trying to explore some of the features of these fictitious forces.